Alright, we're going to cover kinematics and problem solving. This is the second half of section 2.5 and all of 2.6. This is going to include example problems 2.6 through 2.9. One quick warning is that this talk is going to be a little bit longer than the others because we have 2.6, 2.7, 2.8, and 2.9. That's 4 example problems that we're going to work out through this. So what I want you to do is make sure to get your notes. You can take a break or go back and redo or rewatch for your example problems. And the other notes that we're going to do for this section are going to be about lab prep. So, in our previous lecture, we talked about uniform motion where acceleration is 0. And for that situation, pretty much every single time, or not just pretty much, always, every single time, this equation will give you anything that you need to know because there is no acceleration. Remember that it's the change in position over the elapsed time, which when we talk about the elapsed time, we are setting it as time because we can assume that the initial time was 0. There are situations, like you learned in your graphing lecture, that might not be the truth. Right, and then there's uniform acceleration, where the acceleration is a non-zero number, and in that case, acceleration is going to be equal to the change in velocity over time. And we're going to be focusing on those situations today. All right, so I'm going to go over some important symbols. You will begin to see symbols in a very specific format for AP, and remind me in case I forget that you need your equation sheet in class. So the first one, we're going to talk about position, right? Delta x is the change in position, and so delta x is of course made from the final minus the initial. So final position, up to this point in time, I've been referring to it as x2, which we know means the final position, which I can also give in the format of xf, but how you're going to notice it in a lot of AP Physics material is just x. Compared to initial position, which we call x1, it could be xi. I don't know why I wrote a y there. Sometimes I'm a little bit tired. My brain gets leaky by the end of the day, but that should be xi. But in AP Physics terms, you're going to see this written as x0, or the x at the start position. So when we look at the change in position, it's always going to be x minus x0, right? Just like that. And that would be your change in x. One of the things to note is that in any situation, you can use your x as your variable for position. However, most often in the vertical direction, your change in position will be given by y minus y0. And then you're going to notice the same nomenclature for velocity, where delta v is the change in velocity. So final velocity, which we've represented as v2 up to this point in time, could be given as vf or v. So by that logic, it should make sense that your initial velocity v1 is given by vi, but most commonly in your AP material, you're going to notice it given as v0, or velocity at the initial position, which means that your change in velocity is going to be given by v minus v0, the final minus the initial. So now that you know that nomenclature, we can jump straight into the equations. How exciting was that? I'm telling you guys. There's this terrible fly in here, and I may be driven mad before the end of this lecture, just a warning. So, there are some relationships during when we're analyzing uniform accelerated motion that are always true. The first one that we can start with is that acceleration equals the change in velocity over time. If we analyze this situation, right, we can rearrange this equation. And most of the time when you're looking at this relationship, it's actually given in terms of finding the final velocity. So in that case, the final velocity is going to equal the initial velocity plus acceleration times time. So you're probably wondering, how did she do that in her head? Well, I'm going to be honest, I knew this equation, but what I did is I multiplied both sides times time, and then I got AT equals V minus V naught, added V naught to both sides, rearranged the equation, and there it is. So this is known as a kinematic equation. It's useful for any situation that you could analyze under uniform accelerated motion situation. And you notice that this equation has initial velocity, final velocity, acceleration, and time. You don't need to know the position. So if we wanted to know the final velocity in a situation where our initial velocity was 0 meters per second, and we accelerated at a rate of 2.0 meters per second, and that acceleration occurred for a total of 3 seconds. Well, let's consider the math of this situation, because we could use this equation to calculate our final velocity. So this is a situation where a runner, maybe it's you, has decided to start a race. They accelerated as consistently as they could for 3 seconds at 2 meters per second. When we do this problem, make sure to cancel your variables. That second eliminates one of your denominator seconds, and 2 times 3 is 6.0 meters per second. The units cooperate here, and that's what your final velocity equals. If you can run like that, ladies and gentlemen, you're a pretty quick runner. So that's our first equation. The next equation is this equation. You're probably going, gee, Miss B, where did that equation come from? Because our equation for acceleration is change in velocity over time. Well, how about I show you? That seems like a pretty exciting way to live your life. All right, so for this equation, what we're going to do is we're going to consider the fact that we know that velocity equals the change in position over time. All right, remember this, the velocity equals change in position over time. Well, if you look at this format, it's this equation rearranged, just like I rearranged this equation. You should see the relationship. But you're probably saying, well, this equation right here is only valid for situations that involve uniform motion with no acceleration. And that's true, except remember, this is an average velocity. And we know that average velocity in any situation is the average of the two velocities. V naught plus V divided by 2, that would give you your average velocity. So that means I could actually take this and plug it in up here, and if I do that, then x equals x naught plus v naught plus v over 2 times time. So now I have an initial and a final velocity, and I can manipulate this equation so that if I distribute that t, then I could get, or I could actually instead, I could take the final velocity, which equals v naught plus a times t. So I could say x equals x naught plus v naught plus v naught plus a t all over 2 times time. And now I don't have to worry about our final velocity. And if I reduce this equation enough, I'm going to get x equals x naught plus v naught t plus 1/2 a t squared. That's what it equals. And this equation is valid under constant acceleration. Most of the time when you see this equation written, you can rewrite it in the form of x equals v naught t plus 1/2 a t squared. right? And this is valid anytime you don't have your final velocity. Right, and that was just done with some simple substitution. You're not going to have to do that simple substitution. I just want to show you how we can manipulate a situation using concepts that we know are true to develop equations that we can analyze. We can find the position of an object that's been accelerating as long as we know what its initial velocity was and how long it was accelerating. We could, on the other hand, if we knew the position, we could calculate the initial velocity if we understood how much time had passed and what the acceleration was. We only can't solve for final velocity in this situation because we don't know what the final velocity was. That fly, I'm telling you, I will destroy it one of these days. So that brings us to other derived formulas. Remember, they're derived because they come from the relationships that we just went over, right? These other formulas are always going to work for uniform accelerated motion. Anytime acceleration is happening uniformly, that means you're accelerating the same way the whole time, which for this class we're going to assume most situations occur in that situation. Then these equations are going to be true. Right? This is the first one that we derived. The final velocity is going to be equal to the initial velocity plus acceleration times time. This equation is convenient for calculating when one of the variables is unknown and you don't need to know or do not care about the position. This equation, which is the other one that we derived, is going to be useful for you to calculate position, initial velocity, acceleration, or time if you don't need to know, do not have access to, or do not care about the final velocity. Likewise, this equation can be derived. Right? This is a situation where you could analyze the relationship between acceleration, position, initial, and final velocity, and you don't need to know or don't need to worry about how much time the situation took. This is another situation where you can analyze the average velocity and the relationship between position and average velocity. This is the equation that I'm referring to here. If you know your initial and your final velocity and you know the acceleration was uniform, then this is the relationship between your initial final velocity, time, and your position. You don't need to know acceleration in order to consider how this object moved in relationship to initial, final velocity, position, and time. Hey look, here's this equation again. I must really like it because I wrote it down twice. And then here is, if you consider this equation and then consider this equation, you could see the logic in both of these relationships being true. Right? If you know your initial velocity but don't know your final velocity, you could find position using this equation or find the relationship between the variables using this equation. If, however, you don't know your initial position, then by logic, the final position and the final velocity is going to have the same relationship but opposite of the acceleration. So you can use this equation if you don't know the initial velocity. Alright, so those are your kinematic equations. You do not have to memorize them. They will be available to you on any equation sheet for the AP test. They'll be available to you for testing and quizzing in the class. You just need to know how to apply them and use them. And so we're going to go over some example problem solving in this class that uses these kinematic equations. Please keep them handy since you've written them down because you're going to be using them in order to solve the examples. First example we're going to do is a runway design. Alright, so the book tells us that we're designing an airport for small planes because we have lots of money and want to spend it flying. That kind of seems to be what rich people do with their money. I know that I would, because I would rather fly to the North Coast than drive there, seeing as that would save me several hours and make me slightly more awesome than I already am. So in this situation, one kind of airplane that we're going to use in the airfield has to reach a minimum speed before takeoff of 28.5 meters per second. Right? This is the minimum speed for successful takeoff. What's the point in building a super awesome airport with a runway if your planes can't make it off the ground? All right, so what we want to do is we want to propose a 150 meter long runway, but this plane has an acceleration set, like this is the maximum acceleration that this plane can achieve, and we want to see if it will fit on our 150 meter long runway. All right, so here's our runway. It's 150 meters long, and we want to know, can our plane, this is what my plane looks like. It's like a fish with a nose. All right, we want to know if it starts from rest, will its final velocity be this when it makes it over here if the acceleration is 2.0 meters per second per second. Well, now let's consider this situation, because I gotta tell you, I don't know just by looking at the numbers if that's going to be achieved, and I don't want to go second by second and say, well, in the first meter it's going to be traveling at 2 meters per second, and in the second it's going to be traveling 4 meters per second, and then extrapolate so on and so forth. That seems like a pain. Instead, I want to consider the relationship between position, acceleration, and velocity. If I'm going to consider the relationship between position, acceleration, and velocity, guess what I don't care about? I don't care about, who cares about time? Right? I don't care about time. And if I go back and I consider which equation does not give one little poopy stuff about time, it's this one right here. So this equation is the relationship between all of the possible variables. V squared equals V naught squared plus 2ax. This is the relationship between initial final velocity, acceleration, and position. So the first question I'm going to ask myself is, how fast is my airplane going to be going on a proposed 150 meter long runway? So I want to know, or I want to find, the final velocity. Given that my acceleration is 2.0 meters per second, my position change, or my total displacement, is going to be 150 meters down the runway, and that my initial velocity, right, all airplanes when they take off, they start from rest. So I can plug all of those in, and I'm going to solve for x. So, or I'm going to solve for v. So here we go. V is going to equal the square root of 0 plus 2 times 2 meters per second times 150 meters. Alright, so now I'm going to end up with velocity equals the square root of 2 times 2 is 4. 4 times 150 is 600. And my units are meters times meters is meters squared, seconds squared. So when I take the square root of that, I'm going to end up with 24.49 meters per second. I check my sig figs. I'm able to give 3 significant figures, so my final velocity is 24.5 meters per second. And I gotta let you know, this airplane is not taking off. This is a sad crash waiting to happen, because this velocity right here is not the velocity that this plane requires in order to take off. So sucks for you. I guess we better figure out how long that runway actually needs to be in order for our plane to take off, so we can go and have awesome vacations like rich people should. So back to rich people problems. We need to know how long our runway is actually going to be. So this time we're going to be finding the actual displacement that the plane needs to be. And so that's what we're going to find. And this time we know that if the airplane is going to take off successfully with an acceleration of 2.0 meters per second and a final velocity that it needs in order to take off of 27.8 meters per second. That's the minimum speed for successful takeoff. And it's starting from rest because that's how all planes start. What will the position be? And we still could care less about the time that this takes. We could find time, but we don't really care. We don't need it to answer this problem about how long to make our runway. So we have this equation, v equals v naught squared plus 2ax, and this time we're solving for position. So I'm just going to rearrange this equation to be v squared minus v naught squared over 2a equals x. And then I'm going to plug in my variables. So I get 27.8 meters per second, and that value is squared all over 2 times 2.0 meters per second squared. All right, when I do this, all right, I have to square my velocity, 27.8 squared. All right, and that gives us 7.73 times 10 to the 4th meters squared per second squared. Remember that your units get carried through like variables, and that's divided by 4.0 meters per second squared. If we take care of our units, our second squares are gone. This meter is gone. One of those meters is gone. So when we're done with this problem, we're going to end up with a value of, hold on, I need to re-crunch my numbers, 27.8 squared. I did something funky here. This number should have been 772.8. Forgive my maths. So we divide that by 4, and we end up with a value of 193 meters. Alright, that's what our minimum length is going to be, and since nobody likes measuring out exactly that number, and we are so rich that we're buying planes and taking off in them to go on vacation, we're going to say that we recommend that this runway would be about 200 meters. Right, because if we're rounding, and I would even say, we'll say it should be 2.0 times 10 to the second meters. I'm going to say 2 significant figures is going to give us an accurate enough, a long enough runway in order for this to take off. If you reported an exactly 193 meter runway, you would be mathematically correct, but every single time you take off, you would have to hope that your pilot, or you if you're driving, keeps your foot on the gas pedal and accelerates perfectly uniformly each time. It's nice to have a couple extra meters for takeoff. So you're going to notice that on this, I actually kind of followed a little bit of a pattern. I had this picture up here. I identified what I knew and what I was trying to find. I identified my equation. I plugged things in. I solved them. Most of the time when I was being super responsible, I put boxes around my numbers. All of that organization wasn't by accident, and it's going to turn out that you need to make sure that your organization is also not by accident. And so we're going to go over section 2.6. Section 2.6 is all about solving problems with an organized approach. One of my biggest recommendations to you is that if you're solving problems in physics, please support the lumber industry. There is a huge amount of lumber throughout Oregon and Washington, and it's a renewable resource. People's jobs depend on it. They're making sure that they're harvesting trees environmentally sound. So please use that paper to clearly organize and take up all the space you need when you're solving your physics problems. Do not do not write tiny and all over the place. Organize your work. Organization is not an accident. The better organized your papers are, the better grades and the bigger smiley faces I'm going to give you. So, when you're solving a problem, even before you start writing things on the paper, make sure you're focusing on all the details, which is just another way of saying please, please, please read through the problem carefully. Make sure that you understand what all of the variables are. Make sure you understand what the situation is. Make sure you are aware of what you're solving for. I can't tell you how many times I've seen people who don't get a problem correctly, not because they did something wrong, just because they didn't solve for what they were supposed to solve for. An answer that's mathematically correct or physically correct does not necessarily answer the question that you were asked. So make sure, read and reread. Focus on all those details. All right? Choose your study parameters, which means make sure that you are making a good decision about what you're solving the problem for. Decide what your object is. Who's the guy, for kinematics, who's the guy doing the motion? Is it a plane? Is it the spot? Is it the spherical cow? Is it Benny? Make sure you know who your object is. And make sure that you are aware of what time frame this is happening in. The elapsed time is going to be a major variable in solving a problem correctly. All right, if your object is Benny, Benny's got a nice little hat. Benny's in a good mood today. There he is. So here's Benny. Benny. Benny is levitating as always. And Benny is our object. Benny goes all over the place. In fact, sometimes you don't always know where Benny is, so make sure you are aware of what time you are analyzing for Benny, because yesterday Benny was in a different position, undergoing different motion than he is today. Right? You're going to draw it, and you're going to notice that I already started drawing even before I started to show you this section. I mean, seriously, don't be lazy. I know we do a lot of problem solving. Drawing seems like an extra work. I draw pictures for everything. I make you little cutouts. Don't be lazy. Draw your situation. I don't care if you draw a full-on Benny or if you draw a tiny little spherical cow. I don't care if your spherical cow is represented by a little dot. Just make sure you're drawing it out. Don't be lazy. Set your coordinates. Benny is traveling this way. I've decided that this way is the positive direction. Right? I have established my time parameters. Right? So I have established which direction's positive, which direction's negative. I can be consistent with that now. Every time Benny moves to the right, Benny is moving in the positive direction. Every time Benny is moving to the left, Benny is moving in the negative direction. I can establish what time frame I am analyzing. And I can make sure, because I have it written down to refer to, that I am being consistent. Then we're going to record our knowns and what we desire. All right? When we record our knowns, you can actually make a list of knowns, or what you're more familiar with, the terminology you might like a little bit better, familiar, is called givens. All right? And you also want to be very specific about what you're trying to find. In fact, you should write down what you're trying to find first, because that's the whole point of doing the work. All right? So make sure you record your knowns and your desired variables that you're trying to establish. And you can translate. In physics, most of the time, or every time, starting from rest means that your initial velocity v0 is going to be 0. You can give it units, because even zeros have units. I started to write this word there. I spelled it really incorrectly, so I wrote down words are hard. But if you see the terminology came to rest, or is coming to a rest, or will come to a rest, then that tells you that your final velocity is 0. The zeros have units. Alright, so that means you're going to record your knowns, your desired variables, and you're going to translate any of the language in the problem so that it's represented in that format. So we're going to say Benny had an initial velocity of 0 meters per second. He had a final velocity of 10 meters per second, because Benny can move very quickly. He's a levitator. You don't want to make him angry. You don't want to see his evil Benny side. We want to know his time. We want to know how long it's going to take before Benny torments your soul if he has an acceleration of 6 meters per second. So now we've really established that we're looking for the relationship between initial and final velocity, acceleration, and time. All right, once we've done that, all right, decide what physics actually apply in the situation. All right, so you look at it and you go, okay, which concepts are true? Right now we're only studying the concepts of motion, uniform accelerated motion, so we can consider all of the relationships that are true. So in this situation, all right, we're looking at Benny. Benny is accelerating, so we can assume that this is a uniform accelerated motion situation. That is the physics. Any of the physics that applies for uniform accelerated motion are going to be a valid way to analyze the situation. So once we've analyzed the situation, what's going to work, we can pick equations that we plan to use, and we can verify that those equations are actually going to work for our situation. So we're going to be using one of our kinematic relationships that works for any uniform accelerated situation. And I'm trying to pull them up, not because I don't remember them, but because I wanted to give you the visual. All right, for uniform accelerated motion, like what Benny's doing, we're looking for that relationship. We don't need to know position. We only need initial, final, and time, because we want to know how long is it going to be before Benny torments our soul. So that's the equation that we're going to use for Benny. All right, so we pick our equation. We make sure it works for our situation. This is an equation that works for uniform accelerated motion, so it's going to work just fine for us. And then we're going to, one of the things that I want you to know is sometimes it might take more than one equation, right? We might need to first find time and then apply it to a situation where once we have that time, we have to solve another problem. Or you might need to find a system of equations. You don't have a stopwatch, you couldn't count, so you might have to substitute in another true equation to find that. And system of equations is going to become very important when we do projectiles. So if you don't know what a system of equations is, make sure to ask about it in class and we will talk about it. All right, then we're just going to calculate. And make sure when we calculate that we have enough significant digits to have correct significant figures at the end. So our final velocity was 10.0 meters per second. Our initial velocity was 0 meters per second. Benny accelerated at a rate of 6 meters per second every second. We'll say that it was 6.0 meters per second every second, and that happened for a certain amount of time. So now we're just going to crunch our numbers and we're going to solve for the time that it took Benny to torment your soul. And it's going to be 10 meters per second divided by 6, and that's 10.0, divided by 6.0 meters per second. And when we do our math and cancel our units, meters are gone, these seconds are gone, one of these seconds are gone. If you have a fraction in the denominator, it then moves to the top, so our time is going to be 10/6, or that would be 1.6667 seconds. We can carry two significant figures, so we're going to say that it will take Benny 1.2 seconds to torment your soul. So we've calculated, right? We've kept enough digits to have correct significant figures. Now we're going to look at our answer and we're going to consider whether or not it works. You can use an order of magnitude to decide whether or not it works, or you could just look at it and you could say, well, okay, Benny's accelerating from rest 6 meters per second every second. So that means in the first second, he's traveling 6 meters per second. So he has covered about 3 meters of distance. And in the second he will have covered about the difference between 6 and 10 is he's done another 6, 3, so 9 meters per second, and he's covered another 4.5. So it seems reasonable. In 1.7 seconds he's going to be sped up quite a bit. And then you're going to check your units. Checking your units is another thing that I've seen people skip steps on. Notice that I write down my units and I resolve them every time. Sometimes you can figure out an answer just by working with the units. All right, so in this equation we had time equaled velocity over acceleration. Right, so we had meters per second over meters per second per second. And when we resolve these, look, meters per second and meters per second cancel out. You have a fraction in the denominator, which when you move it becomes the numerator. So here, taking a look and making sure our units match, said, oh, we were trying to find time. Time is in seconds, so this is going to work great. Alright, so that's our problem solving method. What we're going to do now is I'm going to break it down for you even further in our example problems. And I'm going to show you this format. You can actually draw the boxes when you solve problems. Alright, so what I want when you do problem solving for kinematics, you should have a picture. You should make sure to establish what your knowns are and what you're trying to find. You find your equation, you solve it, and make sure that your answer is highly visible with correct significant figures. So we're going to do example 2-7 in order to practice this format of problem solving. And you believe me when I say that this format of organizing your work and taking up all of this space, right? You're not a tree hater, you're supporting the lumber industry, and you're making sure that you are successful in your problem solving. So we're going to do 2-7, the acceleration of a car. And we want to know, how long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second per second? So we want to make sure, reread the problem, make sure you understand it. Make sure there's a time period. All right, so we want to know, how long does it take? So we're trying to find time. Right? And then we want to make sure that we have all of the other parameters. How long does it take? Well, the car is going to travel a position. It's going to have a displacement of 30.0 meters when it's done. So here's where in our picture we're going to establish our coordinate system. I'm going to say that the car is traveling in this direction. I'm going to give it, it's a good looking car. Here's you. You're trying to drive far, far away from Betty. And this car is going to cross this intersection after the light turns green. So that means that when you're sitting at an intersection and the light hasn't been green, your initial velocity is almost always 0. So our x equals 30.0 meters. Our initial velocity is 0 meters per second because that's how fast you're going before the light turns green. And the car is accelerating in this direction, so in the same direction as your final velocity, with an acceleration of 2.00 meters per second per second. So we also have an acceleration of 2.00 meters per second per second. And we don't know what the final velocity is, but what we really want to decide is, do we need to know what the final velocity is? And the truth is, we're getting asked for time. So I could say, who really cares about final velocity? We're not going to need to know final velocity in order to solve this problem. So now we're going to consider, now that our diagram is drawn, and we have our knowns and we know what we're going to want, well, let's see. This object is accelerating, so this is a situation where we can apply any uniform acceleration situation. We're not looking at what happened before the light turned green. We're only looking at what happened once the light turned green and the intersection was crossed. So we don't need to worry about how long you stayed at rest. We just need to know once you started moving. So we're going to look for the relationship between initial velocity, acceleration, and position. All right, and our equation is going to be that the position is going to be equal to the initial velocity times time plus 1/2 acceleration times time squared. All right, that equation we can solve for t, but take a look at it. This equation uses everything that we want to know, but it's got a t and a t squared. So if initial velocity has a value, we would have to use Pythagoreans. But lucky for us, look, initial velocity is 0 meters per second. So 0 times time is 0. So our position actually equals 1/2 AT squared. Now we plug in 30.0 meters equals 1/2 times 2.00 meters per second squared times time squared. You could first isolate the variable time and then plug in. I'm okay with either way, but here I'm going to resolve it. It's going to be time is going to equal the square root of 30. And here for units, right, I'm going to have 30 meters divided by meters per second squared. So meters are gone. A fraction in the denominator becomes the numerator, so we're looking at the square root of 30 seconds, or 5.48 seconds. All right, that's what t equals. And you put it in this box. You could, if you had solved for this, right, if you had taken the square root of 30 and you got 5.4772, right, and this is seconds, all right, you can write the answer there, but then make sure to take care of your significant figures before plugging it into your final answer box, and make sure that your final answer is highly visible. All right, so that's example 2-7 of using this system. Let's apply it again for example 2.8, where we're going to be looking at airbags. Right? Airbags are a really neat thing, in case you didn't know. They can save your life or save your brains or save some of your vital functions if they're used correctly. But one of the things that it's important to know is an airbag doesn't work unless it inflates before your face crashes into your steering wheel and destroys that brain that's inside of you. All right, so in this situation, we're going to consider designing an airbag that can protect a driver in a head-on collision at a speed of 100 kilometers per hour. So 100 kilometers per hour, which is 60 miles per hour, you're probably ultimately going to be converting that in meters per second to keep things in SI units, which you're always going to need to do when you're using kinematic equations. We'll worry about that when we start recording our givens. Right now, we're just going through and interpreting the situation. So we're going to estimate how fast the airbag must inflate to effectively protect the driver. And then we're going to take a look at how a seatbelt helps the driver. So analyzing that situation, one of the things we know for sure is we're trying to find the time for the airbag. Right? How fast does the airbag need to inflate to save the driver's brains? All right, so we're going to assume that acceleration is constant, because then we can use our uniform accelerated motion equations. And we're going to be trying to find t. Now, there's two different equations that allow us to solve for t. One of the things that I want you to consider is what do we know? Do we know the initial velocity or the final velocity? Do we know both? Which one is more helpful? All right, we don't know what the acceleration is. And I know that if I want to find time, it would be really useful to find acceleration. All right, so here's what's happening. We have a car. And this car is traveling at some speed over distance x. And then this car crashes. All right, and that airbag has to inflate when it crashes. We don't want the airbag to inflate here. We only want the airbag to inflate right here during the crash, which means that when we consider this situation, we only want the time here. We only want the time it took for your car to crumple. So that means that we can choose our time interval to start when the car begins the crash, and we want that time interval to last for the entire time that it takes your car to crumple up. This area that crumples up in the hood, that's called the crumple zone of the car, and it just so happens that the crumple zone of the car is about 1 meter in most cars. So now we've actually got a few variables that we can list out that we know. Our knowns are that the crumple zone is 1.0 meters. We know that the initial velocity was 100 kilometers per hour, which we're going to convert into meters per second. All right, and our conversion for kilometers per hour to meters per second is 100 kilometers per hour times 1,000 meters per every 3,600 seconds. All right, so that's going to give us 28 meters per second for our initial velocity. We also happen to know our final velocity is 0 meters per second. All right, you stopped. That's what happens when you crash into something. We don't know what acceleration is. It seems like it might be a little bit convenient for us to find acceleration in this situation. So let's go ahead and let's do that. Let's find the acceleration. I'm going to use the relationship between position, initial, and final velocity in order to find acceleration. All right, so that means that our acceleration is going to be v equals v naught squared plus 2ax. I'm going to solve for a. A equals v minus v naught. Both of those values are squared, all divided by 2x. So that's going to be negative 28. Or it's just going to be negative 28 meters per second. Alright, and that value is going to be squared, all divided by 2x, which is 2.0 meters. Alright, and that's going to give us an acceleration of negative 390 meters per second squared. Alright, checking my units, I'm going to make sure. Alright, that becomes meters second squared. That meter cancels with one of those meters, which gives us 1 meter and seconds squared. So that's our acceleration, which we can now record up here as negative 390 meters per second squared. You can also report that down here. All right, that direction. All right, that direction comes from the fact that we had v minus v naught, and both of those values were divided by 2x. So that means that it's a negative overall value. All right, that means that the acceleration happened this way in the picture. All right, it happened in the opposite direction to the velocity. So now that we have acceleration, we can solve for time. I'm going to use our equation of acceleration equals v minus v naught over t. I'm going to rearrange it to solve for time. Time equals v minus v naught all over a. So when I plug in values there, it's going to be 0 minus 28 meters per second divided by negative 390 meters per second squared. And that's going to give us time, which is 0.07 seconds. So here is definitely an example where we want to make sure that we've solved for both of the unknown variables, and we want to make sure that we're answering the question that's asked, how long is it going to take? The next to follow up is, what does the airbag do? Well, the airbag spreads the force over a large area of the chest to avoid puncture of the chest by the steering wheel. It also avoids puncture of the face by the steering wheel, depending on your height. So people have actually lost portions of their forehead or fractured portions of their skull from landing their face into an airbag. Little quick aside, it's actually hydrazine, which is a rocket propulsion fuel that is used in a lot of the airbag immediate inflations that causes them to be able to fill up at such a rapid rate. The seatbelt keeps the person in a stable position regardless of what direction the car crashes in, so that you're hitting the airbag directly on. This prevents certain types of whiplash injuries and usually minimizes broken necks in that situation. So that brings us to our very last example, example 2-9, braking distance. This is a doozy. So let's go ahead and let's go over the situation. All right, we want to estimate the minimum stopping distance for a car, which is important for traffic safety and traffic design. Right? If you don't know how long it takes a car to stop, then you don't know where your safe stopping distance is. If you've ever noticed somebody ridiculously slamming on the brakes and not making it through the intersection, or I've actually seen somebody slam on the brakes and end up stopped in the center of the intersection, those people had no idea what their stopping distance or stopping times were. All right, so we want to look at what the minimum stopping distance is for a car so that we can make sure to design our streets and roadways so that they don't accidentally cause people to stop and land in the middle of the intersection, which would cause people to get into more car accidents. All right, so what we need to consider here is, what does it take to stop? So imagine here you are. You're driving fast because you're still trying to escape Benny. This is you. Benny is catching up to you. And Benny is sad because you're running away from him. So look out. You're traveling with a speed, we'll give you a consistent speed of 14 meters per second, and you're traveling in this direction. Which means that we've established our x-axis. Over here, you're going to be stopped. Alright, so we need to consider everything that has to happen to get you to stopped. Alright, in order for you to stop, we have to consider the fact that it's going to take you a second to realize that you're stopping. So in order for you to realize that you're stopping, or that you're going to stop, there's going to be this amount of time here. Right? We call this reaction time. And for reaction time, you're actually experiencing uniform motion. You're traveling that same speed. You haven't realized that you need to put the foot on the brakes, right? Which means that your speed is constant. You aren't accelerating. You aren't decelerating, right? And then once you realize that you need to put on the brakes and move to do so, right? This is the section where you're going to actually be actively accelerating, decreasing your speed from 14 meters per second to 0 meters per second. Now, I got that 14 meters per second as a handy dandy little tip from the book. I know that this is stopping time, so I know that our final velocity is going to be 0 meters per second. And then there's a few other things we're going to need to break this down. We're trying to find stopping time. All right, we're breaking it up into two sections. The amount of time it takes you to react, so we're going to call that time reaction, and the amount of time it will take you to completely stop once you do begin braking, so that'll be our time stop. All right, which means that our T is going to be our total time of both of those. That's what we're actually trying to find. What we know, or our givens, we know that our initial velocity is 14 meters per second. We know from the book that the final we know because you stop that our final velocity is 0 meters per second. We know from the textbook that our acceleration is -6 meters per second, and we'll say that's 6.0 because that's what the book says, and it's meters per second squared because it's acceleration. We do not know our stopping distance, and we do so. Here I am wrong. We're not finding stopping time, we're finding stopping distance. So here's a really great example of where you need to read and reread the problem to make sure that you're finding the correct variables. So we have the time it takes for you to react, the distance it will take you to react, or the distance you will cover before you react, the distance it will take you to stop once you've reacted, and the total distance. We're trying to find position change, not time. So now that's done. We have our knowns. So we need to break this problem into two different situations. We're going to have a part 1 and a part 2. So here's part 1, here's part 2. Part 1, we're just looking at how far you travel before you even begin braking. Part 1 is uniform motion. That's the physics concept that's going to apply because you're not braking, so there's no acceleration. Part 2 is going to be uniform accelerated motion because that's when you begin to brake and you begin to slow down. And hopefully you finish slowing down before you crash into anything. So for part 1, we know that our reaction time, so our TR, is 0.5 seconds. That's again given by the book. All right. Part 2, we don't know time, but we might not need to know time. So let's consider for part 1, let's first figure out what distance we're going to travel. All right. So because uniform motion applies, we just need to know that velocity is going to be equal, our final position is going to be equal to our initial position plus final velocity minus our final position is velocity, initial velocity, sorry. Position is going to be equal to initial velocity times time. That's all we need to know. Our initial velocity and our final velocity are the same. So that means that our first part, in the first 0.5 seconds, we have 14 meters per second times 0.5 seconds is going to equal 7 meters. All right, that's the position that 7 meters is how far we're going to go before we even realize we need to, or even before we can even get our foot onto the brake and begin our deceleration. All right, so that was a simple thing to find because it's the relationship of velocity equals change in position over time. All right, so we have an initial position we set to 0. Our time is 0.5 seconds. Our velocity is the same the whole time, 14 meters per second. So we solve for 7 meters. Next, we need to figure out what distance we cover, what displacement we have in the second situation. In the second situation, we don't know how long it took. And maybe we don't even need to worry. Who cares about time? Because we have a relationship without time, and that is that the final velocity will be equal to the initial velocity times or plus 2ax. All right, this is the relationship between initial velocity, final velocity, acceleration, and position. We have acceleration, we know our initial and final velocity, so we can rearrange this equation so that we can solve for position, and that's going to be v squared minus v naught squared all over 2a, and that will give us x. So that's going to be 0 minus 14 meters per second, and that's a squared value all over 2 times negative 6. Notice that it's going to be a negative and a negative, so our final position answer here, right, this is the position of stopping. That is going to be a positive value, and that positive value is actually going to be 16 meters. All right, so the amount of displacement we have while we're stopping is 16 meters. The amount of displacement we had before we were able to react was 7 meters, so that means our overall position is going to be the 7 meters before we reacted plus the 16 meters once we were reacting, and that's going to give us an overall position of 23 meters in order for us to react. It's funny. I gotta tell you that right at that moment I came pretty close to asking, are there any questions, as though you would be able to ask me those questions. So please make sure, if any of this didn't make sense, especially the parts where I started to do something and crossed it out because I'm getting tired, make sure that you ask those questions. We're going to take a look in class from this example at the figure 216, the graph for velocity versus time, and how we broke that up. So that concludes our sections. We're going to start following objects next, but before that we're going to be doing a lab.